All right. Hello, everyone, again. Welcome to our tutorial, the modern treatment of the Primal-Dual framework for online resource allocation. So as Vahide mentioned, the tutorial has two parts. I'm going to do the part one, and Rajan is going to go next and do the second part, maybe the more interesting part. So we have different goals from this tutorial. Personally, I have one goal from my part. So the goal is that you walk away from this virtual room having a feeling or maybe an impression that now you understand a lot of these papers in the online bipartite matching literature with the sophisticated primal dual analysis and designs of the algorithms. So that's my goal. And Rajan is going to talk about more interesting stuff. Speaking of which, so when you think about designing online algorithms, in particular for resource allocation problems, typically you think about a benchmark. And then what people have been doing in this literature, I'm going to go into details soon, is writing a linear program, LP, for the best thing you can do in this online problem, as if you know the entire problem instance. And then you try to design an algorithm and find a way to analyze its performance. In particular, you typically care about competitive ratio, which is basically the ratio of the performance of the online algorithm over the benchmark that I have in the first bullet. And one common technique that people have been using proved to be very helpful and successful in this literature is Primal-Dual, which I will explain in a second. So in this tutorial, we're going to actually attack both bullets. So in my part, I'm going to actually show you where are these optimal competitive online algorithms that are vast in this literature coming from. Hopefully, it's a different perspective. Next time that you see one of these problems, it might give you a tool to redesign these algorithms from scratch. So I really try to be very mechanical. So I typically don't like mechanical things, but today I want to be very mechanical, and this is intentional because I want to show you like some systematic way to design and analyze this algorithm rather than really like being the smartest person in the room that can come up with these algorithms and the analysis. And then I'm going to show you a little bit to what extent we can generalize this machinery that will help you to design these algorithms. Rajan, on the contrary, is actually going to attack the first bullet. Do we really need actually an offline LP in order to be able to design and analyze these algorithms? In some applications, which will be covered by Rajan mostly, when you have post-allocation stochasticity, it is impossible or hard to have an offline linear program. So what are the alternatives? What can you do? And is there any way that you can set up some sort of LP-free analysis framework for showing the competitive ratio of the algorithms in that, right? So it's like kind of the outline of our tutorial. And to become a little bit more technical, I'm going to show you various models. But all of them are kind of related to this classic seminal paper by Kart Vazirani back in 1990, a model called online bipartite matching. And for the purpose of this talk, for technical reasons that probably I won't have time to go over, I'm going to almost surely focus on fractional matching or fractional allocations. So what is this problem? It's kind of like simple. It comes from a lot of applications of these models. You have some offline site, think of it as supply that is already available. So you can think of maybe advertising auctions, advertisers are sitting on one end and keywords are arriving online. And then there is an ad allocation algorithm, in this case, an online algorithm, that once the keyword arrives, is going to match it to one of these advertisers so as to maximize the reward of the platform. So this model doesn't have any of those bells and whistles. It is the simplest of all. So capacities are 1 on the offline side. I always use the right-hand side as the offline. And then online nodes arrive over time. So once online node T arrives, you get to see the adjacent edges to this online node. And then you can match them, again, fractionally in this talk to one of these guys. And a fractional matching is just, say, a vector like xtj, where xtj is a fraction of this 1 unit of water that is arriving that you assign to each of the offline nodes j. All right, and the goal is basically, without knowing this graph, as the graph is revealed over time, you try to find a fractional matching that is as close as possible to the optimal offline benchmark, which is the maximum unweighted matching if you know the entire problem. And then this model has been developed in the literature. Maybe the most immediate extension is online vertex-weighted B matching, which is basically the same problem as before, but this time I'm going to have capacities instead of one on the offline side. And then each offline node comes with a reward denoted by R1 to Rn. So think of them as the scores that you get if you manage to match this offline node fully. And again, the same thing. So online nodes arrive, you have to fractionally match them. This time you want to maximize the total collected weight from your matching. And then the model that is the one that is probably the practical purpose behind this literature is AdWords or online budgeted allocation. Goes back to this classic paper of Mehta Saberi Wazirani Wazira in 2007 and Buchbinder Naor 2007. And the idea is that basically on one hand, on one side, I have advertisers with daily budgets B1 to Bn, and I have keywords that are arriving online. And then once the keyword arrives, these advertisers are going to basically tell you how much they're willing to pay for this keyword. So you want to fractionally assign this keyword to one of these advertisers so as to you maximize the total collected bits while respecting the budget constraints on the offline side. Right? And there are more complicated models. So the one I actually like, and I'm going to tell you a little bit about in this talk, maybe more than a little bit, is called edge-weighted online matching with free cancellations. So it is this model. So it is basically the same model as the online matching, but this time you have edge weights. So once a node, online node T arrives, it can be matched to any offline node. They have again capacity 1. And RTJ is the reward of edge TJ, which is the score that you get if you assign online node T fractionally to fully basically to offline node J. And again, the goal is to find the fractional matching. It turns out that for this problem, if you just say it as I said, you won't be able to get any meaningful results. And therefore, you need a technical assumption, which is actually quite important, called free disposal or free cancellations in this context, which basically means that you don't really need to preserve this capacity constraint as a hard constraint. Just imagine you can allocate infinite amount of even water to each offline node. But if you exceed capacity 1, then you have to get rid of some so that you always stay within capacity. But in order to do that, you're not going to pay any cost. So for example, if the online node arrives, this offline node is already at capacity 1 because of the previous allocations. You can allocate as much as you want. But if you allocate X amount, you have to get rid of X amount to create room for this new allocation. And this is an assumption that you need in order to be able to have constant competitive online algorithms in this domain, but also in relevant applications in display ad, it has meaningful, there is a meaningful reality that is backing it up. Another model, which is basically the same thing, edge-weighted online matching, this time I'm going to consider cancellation costs, meaning that if to create room, you have to get rid of say X amount of an allocation that has been allocated at the reward level of R, you need to pay a cost, which is this parameter F times X times R. Right? This model has been studied recently in a paper I wrote with my student and my postdoc at the time. And then there is this beast, which I'm not going to go through the details that much because I have an exercise at the end of this tutorial. I wanted to have it written here. When I share the slides with you, you can go over and learn about this model. It's called configuration allocation whole page optimization. So this is one application of this framework in the context of display ads. When pages arrive, let's say a publisher like Washington Post have a new web page that is creating an inventory of impressions. Then an ad exchange platform such as Google AdX is sitting in between and is assigning these pages to advertisers who are willing to receive these impressions. And then the way that typically it works is that for the ad, so for the entire page, you pick kind of like a configuration of how these ads are going to be displayed. And then configurations determine how many impressions each advertiser gets and how much they have to pay, etc. So it's kind of like a very general model that will include everything I'm saying. And this model also has been studied under the free cancellation and also costly cancellation model. Basically, you can allocate more impressions on advertisers than how much they are contracted, but then the extra impressions are going to be lost, right? So I don't expect you to follow all the details of these models. I encourage everyone to take a look at the slides offline to make sure that you understand the differences between these models. The tutorial is going to get simpler, I promise. All right, so some basic assumptions. So we are thinking about an online algorithm design problem, meaning that the input instance is going to reveal to an online algorithm who is making irrevocable decisions. I don't make any assumptions on how the input instance is generated. In fact, you can imagine there is an adversary, maybe oblivious adversary for the purpose of this talk, who decides on this graph up front and then reveals the online nodes one by one, basically the subgraph adjacent to that online node one by one to the online algorithm. So we try to benchmark our algorithms using the notion of competitive ratio. This is a metric that people in this literature are commonly using. And this is basically the worst case ratio between the expected performance of your online algorithms and an offline optimal benchmark that knows the entire problem instance. All right, so this is an infimum over all the instances, and I consider the class of all the algorithms that might be integral, fractional, might be randomized, might be deterministic. So this is why there is an expectation here. Imagine this is the objective value that you consider, maybe the size of the matching, maybe the total weight collected, and this is what the optimal offline gets. And I look at the worst case ratio between it. All right. So just one thing to be clear in this part of the tutorial, I'm going to focus almost on fractional algorithms and deterministic algorithms. In some sense, if I swipe some of the details under the rug, once you think about fractional algorithms, you don't need randomization, which is not completely correct, but forgive me for not giving you all the details. So I'm going to focus on fractional algorithms and therefore deterministic algorithms. In the second part, Rajan is going to tell you about both integral algorithms, fractional algorithms, deterministic, and randomized. So you will see the distinctions more in his part. All right. So this is kind of like the key question we're asking in this talk. How we can design and analyze ideally the optimal competitive online algorithms in this domain. And the moment that you start thinking about these problems, let's say the online bipartite matching, the vanilla version in your head, you see the tension. So these online nodes arrive, you don't know what subgraph is going to be revealed in future. So on one hand, you want to maximize the immediate reward that you get. So that's kind of like what I call the greediness. So you try to be as greedy as possible to get more reward and weight at the current time. But then you might not hedge against this uncertainty in the future. You need to not put all of your eggs in the same basket. That's kind of like the philosophy here. So you try to hedge against this adversary who is giving you different alternatives as the next step and the rest of the problem instance. And the way to do that is trying to put your eggs in different baskets, trying to have an allocation that is more balanced. Maybe trying to almost uniformly allocating this unit of value among all the alternatives. That's like one option. But you can also think about other ways of adding extra balancedness to your allocation, right? And the question is how you can do that. So the idea that I'm building this part of the tutorial on, and I'm going to explain shortly, is that always start from the greedy algorithm. Try to be as greedy as possible. And typically, when you try to design a greedy algorithm, you can do it using a very simple linear programs and online node arrays. Greedy means that match it to either offline node given their available capacities to maximize your immediate reward. So you can set up a very simple linear program for that problem. But don't solve that linear program. Instead, use some sort of convex regularization, basically a convex regularized version of the linear program to add extra balances. Right? And I'm going to show you how you can basically execute this technique in details. And I'm going to start from the simplest of all times. Online bipartite matching when you allow fractional allocation. And let's see how we can actually design an algorithm using this high-level idea of regularizing the greedy algorithm using a convex function and how we can analyze it. All right. So Here's kind of like the algorithm that I have in mind. Let me give you some notations. For example, let's say I have this online node T that is arriving. At the moment that that online node T arrives, the online algorithm has made some previous allocations, right? So you have allocated these online nodes in the past. And because of those allocations, you have a state in the system, which basically is how much of each of these offline nodes has been consumed in the past, basically the remaining capacity of these offline nodes. And let me use the notation yj, to be the total allocations to j from times 1 to t minus 1. Basically, looking at the previous allocations that the online algorithm has made, y subscript j superscript t is going to show me how much allocation has been made so far. And sometimes when it is clear from the context, I'm going to drop t, and I'm going to use the notation yj, right? Cool. So now we are at some time t. You know the state of the system, which is how much capacity you have for each of these offline nodes. So it is tempting to first run the greedy algorithm. So for a second, ignore this red term here. So the remaining is the simplest LP that you can imagine. So you're trying to find an allocation x to maximize summation xtj over all j's. This is basically, so t is one node, you have offline nodes, you're trying to maximize the amount of allocation you can make, subject to, of course, a matching constraint on the online side. So the total allocation you can make is at most 1, because 1 unit of demand is arriving. And for each offline node, you should not exceed the capacity. So the amount of allocation you're making should be less than or equal than the available capacity. So it's like 1 minus yj, right? So it's a very simple linear program. And in fact, this is what I call the greedy algorithm. So if you solve this linear program every time an online node T arrives, you essentially have the greedy algorithm. All right? So now, instead of running the greedy algorithm, we're going to run a different algorithm, which is going to add balancedness to this algorithm through some convex regularization. And in particular, I'm going to think about this function s small f. Think of it as a mapping from R to R, which is non-negative and increasing. And then capital F is just a primitive function of f. So therefore, capital F by construct is going to be convex and monotone. All right. So now this is the regularizer term I'm going to use. It's a separable term across different offline nodes. And then I'm going to use capital F, where the input argument is the final water level or final allocation level of offline node J after you finish your allocation. So it is yj plus xtj. So yj is the current level and xtj is the current allocation. So this term, this summation is going to be the final allocation level. All right. And now you're in the domain of concave programming. So this is a concave program you can solve exactly. And that will give you some allocation rule. It's going to be a fractional allocation rule because the optimal solution of the concave programs is going to happen on some interior point of the top that we are optimizing over. Let's call that x star tj. So my algorithm is basically the following. At every single time, you set up this convex program, solve that. This gives you x star tj for that online node t. And update the states, go to the next time, set up the convex program again, solve it, so on and so forth. And that will give you some online fractional output, right? And when you think about this is kind of like the fact that you have this symmetric concave function across different offline nodes. This is trying to balance the load across these different offline nodes. So this is alongside the idea of adding more balancedness to your allocation. But the question is this really like the optimal thing to do? And I'm going to show you that this is actually the optimal thing to do. And for the experts in the audience, if you're familiar with the balance algorithm in the literature, this is essentially the balance algorithm. I just rewrote it in a kind of like cryptic way using convex optimization, but really like what it does is a water filling algorithm that assigns the online node in a balanced way across offline nodes. All right. So folklore, if you just solve the LP, this is going to be half competitive. And Rajan is going to actually talk about that in even more complicated settings. What I'm going to show you is that this algorithm that I had in the previous slide is 1 minus 1 over E competitive, meaning that it obtains 1 minus 1 over fraction of the optimal offline. And no online algorithm can do better than these competitive ratios. So theorem number 2 was already proved in Niazadeh in 1990, and I'm not going to show you that. Instead, I'm just going to show you the lower bound that you can obtain this competitive ratio. And the question is how you can analyze such an algorithm. I mean, it's kind of a semi-combinatorial algorithm. It uses convex optimization, but also at the end of the day, you're solving a matching problem. How would you do that? And the technique that people are using in this literature is a Primal-Dual algorithm. So up to this point, I'm actually similar to the literature. I'm going to diverge at some point when I tell you how to do the Primal-Dual analysis. So what is the Primal-Dual analysis? So the idea is that, okay, so I have some algorithm. I want to show its approximate optimality. Let's try to look at the benchmark for this problem, which is a linear program, the offline linear program when you know the entire problem instance, and try to find some quote unquote dual certification for the approximate optimality of this algorithm. Right? Mathematically speaking, so I'm going to write down a pair of linear programs. So the first one called Primal. This is basically the optimum offline benchmark written in the language of a linear program. So you're trying to maximize sum over all tj's x tj, basically the cardinality of the matching that you find, subject to the matching constraints for all online nodes and for all offline nodes. Right? This is a simple packing LP. And the dual is going to be minimization program. It's actually the LP for minimum vertex cover. So you have now variables alpha t corresponding to each online node constraint and beta j corresponding to each offline node constraint. And you're minimizing the summation of alpha t's plus summation of beta j's subject to a covering constraint. This time for every edge in the graph that is unknown to the online algorithm, you try to cover the edge by making sure that the summation of alpha t plus beta j is at least 1. And of course, you have non-negativity of the decision variables, both on the dual side and on the primal side. Right? So this is a pair of the linear programs that you have for the optimal offline. Don't get confused between the convex program I showed you and this LP. So this is for optimal offline. That was a simpler program to some extent that you basically solve for each online node to design an algorithm. Now, what we can do is the following. It's called dual fitting. This goes back to classic literature in approximation algorithm. You try to construct dual certificates. Let's call them alpha t hat and beta j hat, such that, first of all, the total objective value that you get on the dual side will be equal to the primal objective value that you get on the algorithm side, meaning that the fractional matching that you created has a cardinality that is equal to the summation of alphas and betas of these dual certificates. So in particular, if x star tj is my online algorithm, I want to make sure that summation of tj, x star tj is equal to the summation of alpha hats plus summation of beta hats. And then the second one is that you try to approximately cover every edge in the graph. So for every edge tj in the graph, you want to make sure that this dual certificate that is created in some wiki-wacky fashion, might be online, might be offline, doesn't really matter, covers every edge by gamma amount. And if, in fact, if you set this gamma equal to 1, this is showing the exact optimality of your algorithm. So this is too good to be true. So the name of the game is trying to find a certificate that will give you the maximum possible gamma. And let me show you quickly why having this certificate will show the approximate optimality of the primal. In fact, the reason is if you look at a dual solution like this, if you divide the dual solution by gamma, then it's going to be actually a feasible dual solution for your dual program. And therefore, I can just invoke weak duality and get the following set of inequalities. So my algorithm is just a summation of x star tj's over all tnj. This is equal to the objective of the dual because of the way that I constructed this dual certificate. Remember, so bullet number 1 here guarantees that the dual certificate objective is equal to the primal objective. And then this is just gamma times the objective that you get through your feasible dual. So any feasible dual in terms of the objective is going to be at least the dual optimal objective value because the dual problem is a minimization problem. So therefore, you get the optimal dual times gamma. Now you can invoke a strong duality of the linear programs or the weak duality and say this optimal dual is equal to the optimal primal. the objective value, optimal objective value of the Primal-Dual linear programs are equal to each other. And that essentially is your opt. So therefore, your algorithm is going to be gamma times opt. Okay. So this is good news. So that means that we have reduced the problem of analyzing the competitive ratio to the problem of searching for this dual certificate. And this is really usually when the creativity comes, like when people want to brag that, hey, I could find this very cool Primal-Dual algorithm or the Primal-Dual analysis. It really means that I could find this very creative way of constructing my duals to show the approximate optimality of your primal, right? And what I'm going to tell you is that, in fact, this process of constructing duals, I don't want to say it's not creative. It's actually creative. However, it comes from a machinery, and that machinery is kind of universal. So you pick your favorite paper in this literature. The recipe I'm going to show you is basically tell you how you can construct these dual variables. It might need a little bit of leap of faith. You need to believe me that this is the case and try to set up this machinery, which is not very clean sometimes. But once you set it up properly, I'm going to teach you how you can set it up properly. You should be able to construct these duals to show the approximate optimality of the primal. And I should have said this at the beginning of the talk. Feel free to interrupt me at any point, unmute yourself, and ask clarification questions that you have. If you have more substantial questions because of the time, maybe we can do it in the break. But feel free to ask any questions that you might have at any point. All right. So let's continue. Our algorithm is a convex program, essentially. So every time that the node arrives, you set up a very simple convex program, you solve it. And now you want to understand what that convex program does. And if you have taken a one-on-one course in convex optimization, you know that, well, so every time that you say convex optimization problem, the first thing that you should do is writing down the KKT conditions for that convex program, because that tells you everything about that convex program, essentially. All right, so on the top right, you see the convex program that we use for our algorithm, which is basically the LP for greedy plus some regularizer term. And now I'm going to try to write down the KKT conditions for this convex program to see what happens. So KKT conditions, so you have, I assume that everyone is familiar, but just to refresh your mind and also do the algebra correctly, I'm going to assign the dual variables theta for the constraint that x is greater or equal than 0. For the constraint, the matching constraint on the online side, I'm going to use the dual variables alpha. And for the matching constraint on the offline side, one for each of these offline nodes, I'm going to use the dual variable lambda. And then this is the Lagrangian function that you can, basically Lagrangian function that you can write down for that single online node T. So it has two sets of variables. So the primal variable is x, and the dual ones alpha, lambda, and theta. And then it is basically the objective value of the convex program. So this is that part, plus the Lagrangified version of all these constraints. So I'm going to have alpha t times 1 minus summation of xtj over all j's, plus sum over all j's lambda j 1 minus yj minus xtj. And then finally, for these constraints, summation over all j's theta tj xtj. All right? So now you can solve a saddle point problem. You're trying to maximize the Lagrangian over choices of x and minimizing the Lagrangian over choices of alpha, lambda, and theta. And this is a convex concave game. You can always find the saddle point. And let's call the saddle point to be x star on the primal side, and alpha star, lambda star, theta star on the dual side. And if you paid attention, I'm using the notation alpha here, but I'm not using the notation beta. And that was actually intentional because you will see in a second that I'm going to actually kind of connect this alpha, the one that you get, to the way that you have to construct the dual certificate. But before getting there, let me write down the KKT conditions. And again, I assume that everyone is familiar with basics of convex optimization. If you are not, believe me that these are actually the KKT conditions. Let me just quickly tell you what they are. So usually you think of KKT conditions as two categories of conditions. So you have first order conditions that set the gradient to be 0 at the saddle point. And then you have the complementary slackness conditions that basically connect the variables, dual variables being non-zero with the primal constraint being binding or not. So the first one is actually the first order condition. So the gradient of the Lagrangian with respect to the primal variable x at every coordinate j should be equal to 0. If you just write it down, take the derivative properly, this is what the equation would look like. So 1 minus little f of x star tj plus yj minus alpha star t minus lambda star j plus theta star tj should be equal to 0 for every j. Right? There are two approaches to follow my talk. Either you trust me that I did the calculation or you try to do the calculation in real time. Pick whichever is working better for you. And then the complementary slackness conditions, they're quite simple. So you look at the offline constraints. Either if you have not exceeded if you have not exhausted the capacity, then the lambda j star should be equal to 0. If you have not allocated the online node fully, then alpha t star should be 0. If you have not allocated along any edge tj, then theta star should be equal to 0. All right? So to make your life easier, I have the convex program on top and the KKT conditions also on top. This is kind of like a reminder for us, including myself, what do these conditions do? Now, your actual task wasn't just like writing down KKT conditions, it was coming up with a way to construct these dual certificates to show the approximate optimality of your prime. And here's a recipe that I think if you look at every single paper in this literature is kind of like following in disguise. I should say that there are alternative ways of constructing these dual certificates. And when I say, if you look at these papers, you will see these dual certificates. That's not exactly correct. You sometimes see different dual certificates. But for each of those problems, this recipe will give you a dual certificate that shows the approximate optimality. Maybe that's the better statement. All right, so you initialize these alphas and betas to 0 at the beginning. I'm going to construct my dual certificates in an online fashion. Basically, every time that the online algorithm is making a decision, I'm going to actually construct my dual certificates, basically for all the edges corresponding to that online node T. Right? And here's what I'm going to do. So once node T arrives, first I solve the convex program. That's going to give me the primal allocation. But also I'm going to compute these convex dual variables, alpha star, lambda star, and theta star. Then I'm going to do the following. So I'm going to set alpha t hat. Remember, so you need to basically tell me what are the alpha t hats and beta j hats. I'm going to set alpha t hat to be the alpha t star, exactly the alpha t star that you got from the convex program. And that's really like the main idea. So setting the online dual alpha t hat to alpha t star. And then how to set beta j hat. This is following a very simple reasoning. So I'm going to update beta j hat by x star tj times 1 minus alpha t star. And in a second, you will see why. This is basically trying to make sure that the change in the primal objective value and change in the dual objective value are equal to each other. And when you think about this is literally like the unique way that you can do that. So the creativity is coming from the setting the online dual to what you get from the convex program. All right? So okay, so let's try to see why this works. And this is actually quite easy from now on. I'm not going to try to be, yes, someone has a question.
So I have one question. So if you're not using lambda j star and theta star tj, then why did you take the constraints into the objective function? You could have left those into the
that's a very
constraint.
great question. I'm going to use them in my analysis,
Okay,
which you will see in a second.
sure, thank you.
All right. So I'm going to show you two things. Step number one, showing that the change in the primal objective value and change in the dual objective value are equal to each other. And I'm going to do that step by step. So every time that the online node arrives, I'm going to show you the change in the primal objective value and the change in the dual certificate are equal to each other. And let's do that. So imagine T arrives. So we are going to allocate following the convex program optimal solution x star. So therefore, sum over j x star tj would be the change in the primal. How much you're changing your dual certificate, the objective of your dual certificate. So you're updating T, so alpha T star on one hand, And then you have x star tj times 1 minus alpha t star. And people try to now use commutator argument, try to say, hey, this is equal to that. I intentionally discourage you to do that. Let's be this boring guy who only understands mechanical algebraic proofs and see why this is correct. So why the delta dual is equal to delta prime. So this is now going to be just alpha t star, I'm rearranging the terms, times 1 minus summation over j x star tj plus summation over j x star tj, right? So this term is the change in the Primal. And I claim that, oh, this should be delta Primal. I'm going to fix this later. So this is the change in the Primal, delta Primal. And then this term, I claim it is equal to 0. And every time I claim anything in this part, you should just look at the KKT condition. So why this is 0? Well, because either x star tj sum over j is smaller than 1, or alpha t star is going to be 0, and this is essentially KKT condition 3. So therefore, this term is 0. This is complementary lattice. And therefore, the delta primary is going to be equal to delta dual. And then when you add up over all times t, that essentially says that primal objective value of the algorithm is going to be equal to the summation alpha t hat plus summation beta j hat. And that's the bullet number 1 that I wanted to show. All right? Step number 2, I have to show you that every edge will get some amount of coverage. And then I'm going to show you actually how you can optimize and find the best coverage. So consider some arbitrary edge in your unknown graph. So let's say an edge t and j in edge set E. Okay, so now let's do the math. So I have to show you that alpha t hat plus beta j hat is greater or equal than the gamma that I'm targeting. And the gamma I'm targeting is 1 minus 1 ray. So writing, again, everything down. So alpha t hat is alpha t star. Beta j hat is at least how the beta j hat at the end of processing on line node t. And what is this? So every time that you updated this beta j hat, you updated based on the optimal solution of the convex program at that time. So it's like sum over t hat less than or equal than t. And every time that you had an update to this beta, you added an amount which was equal to x star t prime j times 1 minus alpha star t prime at that time t prime, right? Good. So I'm going to invoke basically 2 of the KKT conditions at the same time. Let me decipher. So KKT condition number 4 first. That's easier. So this is saying that x star tj might be 0, but if it is greater than 0, then theta star should be equal to 0. And now let's look at KKT condition 1. Just in your head, assume theta star is 0. So this term does not exist. In that case, if I look at 1 minus alpha t star, it's just equal to this little f at this point plus lambda j star. Right? Again, imagine this term is 0, rearrange the terms, and look at 1 minus alpha t star. So it's going to be equal to f at this point plus lambda j star. Right? And this is exactly what I'm writing down here. So I'm replacing 1 minus alpha t prime with this quantity. But when I'm allowed to do that, then x star t prime j is equal to 0. But fortunately, the term that you're actually trying to bound is the product of the two. So by invoking the KKT condition 4 and KKT condition 1, you basically get an equality that this is equal to alpha t star plus x star tj times f of the final allocation at the time t prime plus lambda star t prime j. And this is just the lambda star at that time, like kind of my notation for that. Right? This is pretty good. Now, just some notations. I use the notation yj superscript t for the allocation after you're finishing processing on line node t. So therefore, x star t prime j is yj t prime, there should be a prime here, minus yj t prime minus 1. So this is basically the change in the allocation level at the time t prime. And this quantity is just yj superscript t prime. I'm just using my notations. The lambda star is always greater or equal than 0, and this function is monotone. So therefore, this is greater or equal than alpha t star plus sum over t prime less than t, the change in the allocation level at time t prime times f of the final allocation level at time t prime. And again, I only got this inequality by using my KKT conditions. Now, just like some simple fact about convex functions, capital F is a convex function. So if you look at these 2 points, yj superscript t prime minus 1 and yj superscript t prime, so the slope at this later point is the little f at yj superscript t prime. So therefore, capital F at this point minus capital F at this point would be at most this distance times the slope of this line. This is just a simple fact about convex functions. In other words, this quantity here that you see is going to be at least capital F at the yj prime minus capital F at yj superscript t prime minus 1. All right? And now you look at this and like, oh, it's a telescopic summation because I have exactly the same terms, but the index are off by 1. So therefore, this is going to give me alpha t star plus capital F at the last point minus capital F at the first point. At the first point, there is no allocation. Capital F by construct is going to be 0 at 0 because it's an integral from 0 to x of little f. So therefore, this is the minus term is going to be 0, and this is exactly what you get. Again, I don't want to be combinatorial. I'll try to be boring, algebraic, mechanical. How can I lower bound this further? Consider 2 cases. Case number 1, this yjt is equal to 1. All right? So what is this case? This is basically meaning that I'm looking at some offline node that at the time that online node t arrives, the capacity of that online node was completely exhausted. So in that case, I can say, well, so this is greater or equal than 0. This is 1. So therefore, I have a lower bound of capital F at 1. Case number 2, let's say yjt is strictly smaller than 1. In that case, I'm going to invoke my KKT conditions again, in particular, this condition. So the left-hand side is nothing but just yj superscript t. So if it is strictly smaller than 1, that means that lambda j star should be 0. All right. So now let's go to KKT number 1 and set this time lambda j star to 0. Remember the last time we set theta star to 0? Now we don't know theta star is 0 or not, but we know lambda j star is 0. So set this to 0. All right. What can you say about alpha t star? So move alpha t star to the right-hand side. Imagine this is 0. So alpha t star is going to be 1 minus f of this thing plus theta star. And theta star is greater or equal than 0. So therefore, alpha star is going to be greater or equal than 1 minus f at yj superscript t. But this is important to note that you only can say that if you know lambda j star is equal to 0. And the only way that you can say that is when yj superscript t is smaller than 1. And then you can invoke the KKT condition, the complementary slackness, to say lambda j star should also be 0. Right? So that gives me this lower bound on alpha, and I already had this term. So you have 2 cases, and you probably don't know in which case you are. Then the natural thing to do is trying to choose this function f so that you equate these 2 together. And if you're familiar with this literature, you probably have seen this differential equation several times. You try to find the function f, little f, such that 1 minus f of yj superscript t plus capital F yj superscript t is equal to f of 1, say a constant. This is literally a differential equation. It's a first order differential equation. You can shoot your differential equation technique, maybe use, I don't know, Laplace transform, something like that to solve this, and that will give you this unique solution, that little f of x should be equal to e to the power x minus 1, which basically means that capital F should be the integral of this function, which is e to the power x minus 1 minus e to the power minus 1. All right, and then with this choice of the function, the 2 cases will give you the same constant number, and that constant number is equal to 1 minus 1. And this is kind of a very mechanical way to show this. There are beautiful proofs like Rad Niazadeh dual fitting proof for analyzing this algorithm that even extends to the integral one. But for fractional algorithms, this machinery will give you a very simple analysis without even like thinking through what's happening. And then you might wonder, well, Rad is cheating. So he's showing me this very simple problem that this technique works, but if I just go to, I don't know, like one of these extensions, it's not clear how to do things, etc. So it's not going to work. And I think this is a fair comment, it's a fair question. But in order to prove you wrong, I was thinking about what would be an extension in which I show this technique. Should I go with vertex-weighted matching, which is going to be very straightforward way of extending these, or should I go with something more complicated? So I decided to go with something very complicated. And this something very complicated hopefully will convince you that, first of all, this recipe I showed you can be extended to many settings. And second, hopefully it's going to convince you to sit down, read my slides offline to get to see all the ugly algebra that I'm going to show you in the next 10 minutes or so. All right. Before going to this more complicated setting, I think this is the right time for me to pause. Does anyone have any questions? I'm happy to go back and recap anything that needs explanation.
Rad, can you hear me?
Yes. Yeah, I can
I have
hear
a
you.
quick question. This is just out of curiosity. So you said that you're going to go now to a more complex setting where this also works. Can you give also some insight on where it does not work and why that would be?
That's a great question. So the only settings in this literature that I don't know this, I don't know a variant of this technique that would work is what is covered in part 2. Basically, settings with both allocation and stochasticity. I think there is a paper that needs to be written. I haven't thought about it very carefully. I'm sure Rajan hasn't thought about it very carefully because we had this conversation last week, whether we can find actually a problem that we can attack it from both angles using both techniques. So I'm not sure. I wouldn't rule out the possibility of extending the convex programming framework to that setting. There is another setting in which this technique doesn't work, and that's when you think about integral allocations. I should have said that up front. So this convex programming technique is helpful when you think about fractional allocations, and the counterpart of that in the integral world is when you think about large capacities on the offline side. So if you can have fractional allocations, or your capacities are large, therefore you can do independent rounding of the fractional online algorithms, then these techniques will be helpful. But the moment that you go to the realm of integral randomized algorithms under a small capacity, it's not clear how to extend these settings. Starting from the simplest one, the online bipartite matching with integral allocations. I actually don't know a convex programming based analysis for the ranking algorithm, which is the algorithm that gets 1 minus 1 in that domain. I think this is a very interesting question, and if even that open problem I just mentioned can be solved, I can imagine there will be so many extensions to settings with batching, with cancellations, etc. I think that's something that needs to be discovered. But to the best of my knowledge, this technique only applies to fractional allocation.
Thank you so much. A quick follow-up. Do you have any intuition about how this fares with, say, distributional constraints?
Distributional constraints. I'm actually curious what do you mean by distributional constraints, but maybe we should defer this to the break.
Thank you so much. This is very good.
There was also a question on the chat. Are there nice interpretations for alphas and betas?
Interpretations. Very good. There are, so Alan here has a paper on economic interpretations of Primal-Dual analysis. And at some level, alpha T star is kind of like the utility of a buyer that is arriving online in a Walrasian equilibrium of this matching market, which, if you think about the Walrasian equilibrium, you can think of it as a Fisher market right on the Eisenberg convex program, and then you get the alpha utilities from the Eisenberg convex program. This is exactly the same mathematical object. I think that's one connection I can think of. Economic interpretation. If you paid attention, I'm actually not using prices in this argument, which is kind of like one direction I'm diverging from the literature. So like, for example, if you read Alan's paper, these guys are coming up basically fine interpretation for some prices that people have used in this. So dual variables are prices on the offline side, and the online side are utilities, and then they nicely fit this interpretation with what people had discovered before. But here we don't have the prices. It's just like you get the utilities from the quote-unquote Heisenberg Gale convex program somehow, and you use them here. Yeah, so these are very, very much in disguise. I'm happy to tell you about more formal connections, maybe in the break.
Hello, Rad. I have one small question. If you can go back to
Yes,
the previous slide.
sure.
So when you consider those two cases, in one case, the inequality was tight when lambda tj star was 0. And when lambda tj star was strictly greater than 1, then the inequality better, and we were basically bound, lower bound was not tight. So how does that choice of function e raised per x minus 1? I don't know. I mean, the question is not very well
great
framed.
question. No, great question. In case 2, this is not tight. Remember, so when you're in case 2, you don't know whether theta star tj is 0 or not. The only thing you know is lambda j star is 0. So therefore, if you look at alpha star, it's going to be equal to 1 minus f at x star tj plus yj plus theta star tj. So that's the equality. But then you drop theta star tj because this is greater or equal than 0. So you have a slack here, you have a slack here. It is only, both of them are exactly tight under the correct choice of f when the adversary is shooting you the worst case instance. Otherwise, this is not going to be a tight inequality.
Yeah, so my question was that why that particular choice of f makes it tight? Any intuition?
Why that particular choice of?
Yeah.
I mean, one thing
Is it just mathematics, or I don't know?
Yeah. So on one hand you have a constant, on the other hand you have a function invoked at a point, right? So the first thing is that you need this function to be chosen such that the right hand side is a constant. And the moment that you think about that, the only choice is the exponential function that will give you a constant.
Yeah, I get it.
And
Thank
then,
you.
and then you have a boundary condition, right? And the boundary condition says that f of 1 should be equal to what you get on the right-hand side. And then you solve that, that will give you the constant behind the exponential function. Kind of like roughly how to solve this differential equation.
Okay. Thank you. Thank you so much. Yeah.
Yeah. Cool. All right. So the answer is yes, we can extend this technique. And this is kind of the more complicated setting that everyone hates in this literature. I think it's a beautiful result, but it's sometimes like hard to understand. And I try to make it a little bit more understandable. It's called edge-weighted online matching with free cancellation. So edge-weighted, it's the same setting as before. Now we have edge weights. I'm going to use the notation RTJ for the reward of matching online node T to offline node J. The capacities are 1. We are still going to do fractional allocations. But as I mentioned earlier, in this setting, you need cancellations. So what does that mean? So that means, well, you might be in a situation that an online node T arrives that gives you potential for total allocation of 1. You look at the remaining capacity, you cannot allocate your 1, but you're allowed to. The only thing that you need to do is when you make an allocation to an offline node, if you exceed the total allocation of 1, you have to get rid of some stuff. And the important thing is that when you cancel these previous allocations, these allocations have been made at different reward levels. So you need to be careful about how to encode this, how to keep track of that. So similar to the previous problem, you still need these quote-unquote state variables, but this time they're going to be higher dimensional. So yj superscript t minus 1 r, think of it as the state of the offline node j before online node t arrives. So what does this state encode? This is basically the distribution of the rewards from the previous allocation, the histogram of the rewards from the previous allocation. So imagine I look at all the previous allocations, they have been made at different rewards, and I just like look at the histogram of the rewards that you get. This is the picture that you need to have in mind, and this is encoding the current state of the offline node J. All right, and to make our life easier, I'm thinking of it as a kind of like a continuous density, really. But in fact, this is just a a bunch of like piecewise step functions. But this is easier to think about it as a continuous function. I'm going to swipe these liters under the rug. And one thing I want to mention is that the area on this curve is some number at most 1. If you're at a situation that offline node has been fully allocated, then the area is going to be 1. But you might also be in a situation that you have allocated 0.8 fraction. So therefore, this area is like 0.8. That means that you have room for 0.2. If you're at 1, you don't have any room. But if I give you like extra allocation, you can just get rid of some of these rewards at different points. But you should not exceed the density that you have, because you don't have that amount to get rid of. All right. So another notation, I'm going to use capital Yj superscript tr for the integral of this function. It's like integral from r to infinity of Yj superscript t minus 1 wdw. I know Rajan is going to be upset because we decided to not use notation omega. He's going to use omega for sample path in his part. I'm so sorry, Rajan. I wrote tau first. I realized this is too ugly, so I changed it to omega. So the disclaimer in Rajan's part, we are going to use omega for sample path, so don't get confused. All right, so this is the state when the online node T arrives. Now you have to make a decision as an online algorithm. So your decision this time has 2 components. So on one hand, you need to decide on the new allocations, basically this online node T, how to allocate that to different offline nodes. So I'm denoting that by ZTJ. But as I mentioned, you need to sometimes create room for the new allocation. So you have to get rid of the previously allocated online nodes. And then I'm going to denote that by this XJR, which is basically the state of the offline node J after you do the cancellations. Before you make the new allocation, after you do the cancellation. So you start from some little Yj. You get rid of some of the stuff. That will give you Xj. That's your new state, which is part of the decision of the algorithm, by the way, right? So you decide what to get rid of. So that will define a one-to-one correspondence between Yj and Xj. So this Xj is going to be your state after you get rid of some of the allocations. Now you make some new allocations using Z, and that will bring you to the new state for the next round, right? So both of them are the decisions that the online algorithm should make. We are going to follow the same recipe as before. We start from the greedy algorithm for this problem, which is the one that tries to maximize the reward that you collect in each round T when the online node T arrives. Then we are going to use convex regularization to add balancedness. Because remember, so the goal of this tutorial, the part 1, is to not be as smart, is to kind of like follow this recipe blindly to some extent, to have an algorithm, and also to analyze the algorithm. My algorithm. First step, you need to write down the linear program for maximizing the total allocated weight. Forget about the regularizer term for a second. So this is the linear program I want to solve. Your decision variables are Z and X, right? So the allocation, the new allocation, and the new state after cancellations. So you want to maximize the total reward that you get from the new allocations, minus the reward that you lose because of cancellations. And if you think about everything in a continuous domain, forget about the fact that these weights, the time was discrete, just think about the continuous domain. So you had a PDF YJR, that was your state before you cancel. You canceled some stuff and it brought you to XJ. So the difference is going to be basically the density that you canceled at reward R. So how much did that hurt you, R? So take an integral over that. So that's going to be basically the reward that you lose from offline node J because of the cancellations. And then you sum over all the J's. So this is basically the total reward that you lose because of the cancellations. So if you just want to maximize the net reward subject to the online capacity, the online matching constraints that you have, together with the quote-unquote capacity constraints, then this is going to be the LP that you have. Let me tell you a little bit about the capacity constraint. So the capacity constraint, now you have a new allocation and you have an allocation after cancellation. And the rule is that after you cancel, you should not exceed your 1 unit of capacity. So therefore, ZTJ, which is how much you're allocating from T to J, plus the amount of allocation that you have at J after you cancel some should be no more than 1. And then this is a law of physics. So you are not allowed to cancel things that you don't have. So therefore, XJR for any J and for any R should be no more than YJR. Right? So just one thing that might be confusing in this LP. So Yj is not a decision variable. It's actually a parameter that you have when you start writing this linear program or convex program. The decision variables are X's and Z's. Right? So this, therefore, will give you how you can allocate and how you can cancel to maximize the reward. But as before, we just don't want to use the greedy algorithm. We want to add more balance. And this is what you need to do. It might look a little bit algebraically more complicated, but really like it is the same object as before, mathematically speaking. So what it does is that you use, again, the capital F function. This time, the input to the function rather than the allocation level is basically how much you have allocated more than R for some number R. And then you take an integral over those R's. So XJR is the cumulative allocations from the past, including the cancellation. So this is basically the total amount of cancellation, total amount of allocations after your cancellation at time t that is greater or equal than R. Basically, it has happened at a reward that is greater or equal than R. And then, so you also have ZTJ for allocations that are greater or equal than R, only if RTJ is greater or equal than R. So this is therefore your cumulative after your new allocation. So fancy notation, really. So I give that as input to F, and then I take an integral over all R. So this is a new component that you need for edge-weighted online matching. And these problems that you have allocations at different rewards, but other than that, it's really like the same thing. Right? And this gives you some concave programming. And I can always solve these concave programs very easy. So for experts in the audience, there is this beautiful paper by Devanor, Huang, Corolla, Mirokni, Yan back in 2016. They have some sort of balanced algorithm that will give you 1 minus 1 very competitive. That algorithm is essentially running a specific first order method on this convex program. I don't want to go into the details, but if you're curious, I can tell you later. It's kind of like you run a stochastic gradient ascent, because it's a maximization problem, to solve this convex optimization. And that's essentially the algorithm in disguise that was used in this paper. And the theorem I'm going to show you, not completely, but just sketching the ideas, is that this algorithm is 1 minus 1 very competitive. And the question is how we can analyze that, right? And by now, you should know the answer. We're going to do the Primal-Dual analysis. And the Primal-Dual analysis is going to be conducted through analyzing this convex program by writing down the KKT conditions. So I have the convex program for you here. This time things get ugly quickly, but this framework only needs the leap of faith and consistency. You need to be persistent, try to like finish it until the end, and it actually will give you the answer. All right, so rules of the duality. I'm going to have dual variables theta, gamma, lambda, eta, and alpha for all the constraints in the primal problem. So z greater than 0, x greater than 0, the online matching constraint, and the offline matching constraint, and this physical rule that you are not allowed to cancel more than what you have. All right. Trust me, this is what the Lagrangian would look like. I didn't do anything complicated. It's just bringing this constraint, Lagrangiifying this constraint into the objective. And this is how it would look like. And then the KKT conditions, again, are going to be writing first order conditions plus complementary slides. I'm going to make these slides available so you can check everything offline. So you don't have to, at this point, follow the algebra, but just like the high level picture. You just do exactly what I did as before. And we write the KKT conditions. So 1 and 2 are essentially the first order conditions. So this one is with respect to X. Sorry, this is with respect to Z, which is your new allocation. And this one is when you write down the first order condition with respect to X, your state after the cancellation. And then 3, 4, 5, 6, and 7 are going to be the complementary slackness. Just going over them very quickly, this is basically saying that if the total allocation of the online node is less than 1, alpha is going to be 0. If you haven't exhausted your capacity, lambda is going to be equal to 0. If you have a new allocation on any edge, theta is going to be equal to 0. If you have canceled at any R, then eta is going to be equal to 0. If you have some allocation after the cancellation along at reward R, then X star is greater than 0, and therefore gamma star is going to be 0. So this is kind of like roughly what it says. All right. And again, so we want to do Primal-Dual LP. So don't get confused by these convex programs, etc. So the LP for optimal offline is actually pretty similar to before. So you just want to so the optimal offline tries to maximize the summation of xtj, rtj, or all t and j subject to the matching constraint. The dual is going to be vertex cover, but this time the amount of coverage on each edge is going to be the reward of that edge. All right. And you want to have a dual construction. And the dual construction should certify the approximate optimality of the primal by following the dual fitting framework that I introduced earlier in the talk. And the recipe is exactly as before. So once T arrives, solve the convex program to give you the primal solution. So this is the algorithm. And then compute these dual variables in order to do the analysis. And then the only smart thing that you need to do is setting alpha T hat, the dual variable corresponding to the online node T, to alpha T star, what you get from the convex program. And that's it. The rest is going to be mechanical. You basically, there's a unique way of updating beta J so that the change in the primal and the change in the dual are equal to each other. And what you see on the slide is essentially that unique way. And let's very quickly sketch the analysis. I'm not even going to show you the exact details because it's like too much for a talk like this. But the takeaway is that the rest is almost, maybe I should even like remove the word almost. It is identical to what we had before. It's just like more algebra. And I encourage everyone to follow the algebra when I make the slides public. Essentially, you need to first show a lemma, which is giving you a lower bound on the change in the beta by only using KKT conditions 5 and 6 and 4, which I'm not going to go over. And then you finish the analysis as before. So you basically look at the change in the primal, you look at the change in the dual. They're going to be equal to each other by using the same KKT condition that you used earlier. You look at an HTJ. You want to show that this lower bound is what you want to get. This observation is just like one step, but it's really like cleaning these ugly terms into some compact form. You use the fact that this function f is convex. You have seen that earlier. And then you get kind of like the same analog. So remember, so previously our lower bound was alpha T star plus f of yj. Now it is the same thing, but you just get an integral over capital F at yj tr dr. As if this is kind of like the analog of the f at the final point. In fact, if you think about the step functions, it's a special case of vertex weighted, then you don't need these integrals anymore. But this is the mathematical extension for what you had earlier. And then you will have the same two cases, etc. And then you can use the same differential equation, the same function will gonna show up, and then you get 1 minus 1 over. Right? So let me try to wrap up very quickly. What else can be done with this framework? And there is actually a lot that you can do. So first of all, check the details for the edge-weighted online matching with predisposal. That's pretty similar to what I showed earlier. But as an exercise, I left configuration allocation problem, which includes assortment optimization for the audience in this talk. I introduced the configuration allocation in one of the earlier slides. Take a look at that and sit down and see if you can execute this machinery yourself to analyze this version of the problem, which includes edge-weighted online matching, vertex-weighted online matching, AdWords, assortment optimization, etc. It does not include the extensions that Rajan is going to tell you about with post-allocation stochasticity, except assortment optimization for a technical reason. But it's basically covers everything I showed you. And then there are many ideas that you can think about. What if I change this function f over time? Can I gain from that? Because at some level, you might want to decrease the amount of hedging as time moves forward, because at the end of the horizon, you don't really want to hedge. Can you extend this to a case where a batches of online node arrives rather than just single online node? This question has been studied. What if I change the free cancellation to costly cancellation? Can I use this framework? I actually wrote this paper without the convex programming because at that time I actually didn't know that you can use the convex programming analysis for solving this problem. Expose, I realized it can be done, but it's already too late because the paper is published. So, matching with advice is one other thing that I conjecture this framework can actually be used. There are some recent papers that are exploring this. I'm happy to tell you more. And there are more that I'm sure needs to be discovered. And one of the goals of this tutorial was encouraging you guys to think about some of these questions and finding maybe more innovative applications for this framework.